Hello everyone. This is the final episode in my Common Base Amplifier miniseries. In the previous episode, we introduced the Miller effect, which is a generally undesirable bandwidth limiting effect that plagues circuits like the common emitter. And we introduced the Miller theorem, which allows us to see this effect mathematically and understand it more intuitively. And we introduced and discussed the Cascode circuit, which is a circuit designed to mitigate the Miller effect. Today, we will be demonstrating the common base amplifier by demonstrating how a cascode improves the bandwidth of a common emitter circuit. The goals for this demonstration are to compare the bandwidth of a simple common emitter circuit with the bandwidth of a cascoded version to see that the cascode mitigates the Miller effect and extends the bandwidth. The Miller effect is highest with a high input impedance and a high gain, so we should configure our amplifier accordingly to produce the greatest contrast between common emitter and cascode. In most cascoded amplifiers of high gain, the collector impedance is either active for low to mid-frequency circuits or inductive for high-frequency circuits. However, such structures complicate the circuit, and so to keep things simple, I'm going to use a simple passive resistor as the collector impedance. Finally, because simple passive resistors are a DC impedance and we want high gain, we will need a relatively high voltage rail to handle the DC voltage drop across the collector resistor to maintain a relatively high collector current and therefore a relatively high gain, as gain is proportional to collector resistance times collector current. As I mentioned, most cascoded circuits get around this by having active loads or inductive loads, which present low DC impedance and thus can get away with higher gain without having to resort to a high voltage rail. But to keep things simple, and because the 2N3904 transistor can handle high voltage, we will use a high voltage rail. So we'll start with the common emitter circuit. So here's the circuit, but with most of the values not yet written in. We have a function generator with a 50 ohm source impedance going into a resistive divider. The output of this divider serves as our input voltage. The reason for the divider is to make the input voltage a very small signal. This is important because we're going to design in such a large gain, and so we'll need a small input signal. We will also need to see that input voltage on the scope while measuring the output voltage, but the oscilloscope will have a hard time measuring such a small signal directly, so we'll measure the function generator output, and that will be our proxy for the input voltage. The divider ratio we'll use is an attenuation factor of about 101, because that's easy to make with a 10K resistor and a 100 ohm resistor. Moving along, we have a series resistance from the divider to the rest of the circuit. This is the high input resistance we need to have in order to accentuate the Miller effect's negative impact on our circuit. The divider has a low resistance of slightly under 100 ohms, which is not conducive to showcasing the Miller effect. As a result, we need to add some additional resistance. We're going to set this to 1K, resulting in a total source resistance of around 1.1K. Now let's think about what we want to do for the collector current. As with most amplifier circuits, the decision for each parameter is a fairly complicated optimization problem with many dimensions. To keep things simple, we will choose a fairly arbitrary collector current of 1 milliamp, which is a not unusual collector current. It's not too high, and the transistor has a decent typical beta of above 100 at 1 milliamps, according to the datasheet. It also keeps the transistor's transconductance relatively high, which keeps Rm low and allows us to use a smaller collector resistance while maintaining a high gain. The method we'll use to set the collector current is to use the potentiometer to set the base voltage, run it through a 100K resistor to minimize the effect of the biasing resistance on the input resistance, place a 1K resistor on the emitter, then measure the emitter voltage with a DMM and adjust the potentiometer until we get about 1 volt DC voltage across that emitter resistor, thereby setting our DC collector current to 1 milliamp. The emitter resistor is bypassed by a large capacitance so that at AC frequencies, the emitter will effectively be grounded. This eliminates most of the guesswork on the collector bias current, and so long as the temperature in the room or of the circuit doesn't change too much, this should keep that bias current pretty steady. This combination of collector current and beta does reduce Rpi to some degree, and we likely won't be able to assume that Rpi is much less than the source resistance, so we'll have to take that into account when calculating the gain. Now moving along, we need to think about the collector resistor. Since we want as high a gain as possible, we want this to go as high as possible while still staying within the supply voltage range. Now fortunately, the collector-emitter breakdown voltage is pretty high at 40 volts. As a result, we can push this pretty close to 40 volts and have no problems. My power supply, unfortunately, tops out at around 30 volts, and so I set it to 29.55 volts, which is around the maximum voltage I can get out of my power supply that is stable and usable. So with a 1 milliamp collector current and resistances in kiloohms, that makes the voltages of the transistor nodes pretty easy to calculate. In order for our transistors to behave well in the forward active region, we don't want the collector-emitter voltage to get too low, so we'll decide we want a somewhat arbitrary value of 3 volts or larger, which is pretty solidly in the forward active region. So we want about 3 volts of collector-emitter voltage drop across the common emitter BJT. We also want to reserve 3 volts of voltage for the common base's collector-emitter voltage drop for when we convert this to a cascode, since we want the two circuits to have very similar properties, and we want the same collector resistor and collector current to work for both circuits. We don't need much of a dynamic range above this, as we aren't interested in evaluating the large signal aspects of the cascode. So putting this all together, we get the voltage drop across RC can be up to 22.55 volts. Setting RC to the standard resistor value of 22K gives us 0.55 volts of excess we can use for the AC signal dynamic range in the cascode circuit. Summarizing the DC voltages of note for this circuit, we have the collector voltage sitting at 7.55 volts DC, the emitter voltage at 1 volt, the base at around 1.7 volts, and the collector-emitter voltage therefore at 6.55 volts. Now that we've gotten the basic DC parameters defined, let's derive some of the small signal parameters. So first let's calculate the transconductance, GM, as this is the central small signal parameter. We recall that GM is equal to IC over VT, where VT is the thermal voltage equal to 25.86 millivolts at room temperature, resulting in a transconductance of about 38.67 millisiemens. Taking the inverse of this to get Rm, we get about 25.86 ohms. Briefly deriving alpha and Re from beta and Rm, as we'll need Re when we derive the emitter bypass capacitor, we can see that Re is not much different from Rm as expected. Next, let's talk about the output impedance parameter Ro. In the past, I've calculated Ro from the early voltage Va and assumed Va for a 2N3904 to be about 100 volts. This is because the LT-SPICE simulation model for the 2N3904 has a forward early voltage parameter of 100 volts. However, let's take a look at the 2N3904 datasheet first. From the latest iteration of the 2N3904 datasheet from onsemi, we are provided with a plot of output admittance, which is the inverse of Ro, versus collector current. So we can use this to determine the Ro of our circuit at our selected collector current with greater accuracy than using a constant Va parameter. At 1 milliamp, the output admittance is a little less than 9 micromhos, which translates to around 111.1 K in impedance. Using this value of 111.1 K and the more accurate equation for Ro, we can calculate Va from this, and we get around 101.1 volts, which is very close to the value of 100 volts from the LT-SPICE simulation model, so a pretty good value to use. Keep in mind, however, that based on this plot, if the collector current is too low, that the output admittance is not so linear with respect to collector current, so the effective early voltage will be lower at low collector currents. So the output impedance parameter, Ro, is 111.1 K. The last basic small signal parameter to compute is Rpi, which, assuming our beta value of 100, is about 2.586 K. Let me also formally write Rs here as 1.1 K, as we'll need it in a moment. Now, 2.586 K is not much greater than our source resistance of 1.1 K, so we have to use the more accurate equation for gain, which, recalling from the Transistor tutorial series episode on the common emitter, the full equation for gain is this. Now here we have all the parameters we need except for RB1 and RB2, which are biasing resistors that are not exactly the same in our circuit as the original circuit I used to construct this gain equation. This is very simple to remedy. All we're doing here is taking the Thevenin equivalent impedance of our biasing network and putting it in parallel with Rpi as the total impedance from the base to ground acts as the lower resistor of a resistive divider, with the upper resistor being Rs. Fortunately, the impedance of the biasing network is made to be greater than 100K, and as our pi is much less than 100K since it's less than 10K, we can treat the biasing resistors as effectively being infinite for this gain calculation, and thus RB1 parallel RB2 is much greater than R pi, meaning that when we put that in parallel with R pi, the entire term is approximately equal to R pi. Now, making this approximation to the overall equation, we get this simplified form, which when substituting in all our values, we get a net gain of about negative 498.2 volts per volt. So in spite of the resistive divider made by R pi and Rs, we still have a pretty high net gain. Now, if beta is actually much greater than what we estimated, then R pi might not be much less than the biasing resistance, and thus that approximation would break down. However, we can see that in that case, Rs essentially would be much less than the biasing resistors in parallel with R pi, and thus we would be able to eliminate that R pi over R pi plus Rs term. It would just approximate to 1, and the gain would just reduce back down to GM-RC parallel RO. So the equation is still valid even if beta is much higher than expected. We'll just get a different gain value than we calculated due to the error in our R pi impedance. So now that we have our small signal parameters, the final piece of the schematic we still need to determine are these three capacitances. And to do that, we need to decide upon a frequency range for our amplifier. Since we're just showcasing the advantages of the Cascode, we're going to set our upper frequency to as high as we can go. The lower limit we'll set to 100 Hz. In order to get good properties and minimal phase shifts at 100 Hz, we'll want to set our capacitors so that the corner frequency of the RC time constants produced by those capacitances is around 10 Hz. So we have three capacitors here, and we need to determine what their companion resistances are to determine how large to make these capacitors for their time constants to result in a frequency of 10 Hz or lower. Let's create some reference designators to these capacitors, C1, C2, and C3. First, let's look at the input capacitor C1, which is connected on one side to our source resistance and to the base and biasing network on the other. Really what this capacitor does impedance-wise is it increases the source impedance. So all we have to do is make the capacitor such that the resistive source impedance is much higher than the capacitive reactance at 10 Hz. Our source impedance is 1.1K. So our RC circuit is comprised of that 1.1K resistance and this capacitor C1. So we want the magnitude of the capacitive reactance to be less than or equal to the magnitude of our source resistance at 10 Hz. So we write out this inequality and take the magnitude of each side. Then rearrange to get an expression for C1. Plugging in 1.1K for Rs and 10 Hz for F, we calculate that C1 must be greater than or equal to 14.47 microfarads. So we'll set C1 to 20 microfarads. Moving on to C2, you might be tempted to believe that the companion resistance for that capacitor is that 1 kiloohm emitter resistance. However, that resistance defines the zero frequency that starts increasing the gain from the attenuated gain due to the 1K resistor, down to the final gain with a grounded emitter. So what resistance are we looking for here? The resistance that defines the pole that finally cancels out that zero when the gain hits its maximum is re, as that is effectively in series with C2. So updating these equations for re and C2 and substituting in our value for Re and 10 Hz for F again, we get that C2 must be greater than or equal to 621.6 microfarads. This is rather large, and to optimize this for the high frequency regime, we use a 100 nanofarad ceramic capacitor and a 1000 microfarad electrolytic capacitor to get a capacitance of about 1000 microfarads. Finally, looking at C3, this is merely an AC coupling capacitor to eliminate the DC output voltage when connected to the oscilloscope. So the input impedance of the oscilloscope probe is 10 megaohms. This is quite a bit higher than our other resistances. Plugging it into the same equation as before, we get the much smaller value of about 1.6 nanofarads. We'll set this capacitance to 10 nanofarads, which is quite easy to do and will give us some more margin on this value. We don't want to set it too high or it will take forever for the initial turn-on transient of the system to settle out. So here we have our full common emitter lab setup. Before we move on to the demos, let's go through the setup for the Cascode first. Here's the Cascode, essentially the same as the common emitter, except we've inserted a common base in between the collector of the common emitter and the 22K collector resistor. First, we note that I've added another potentiometer plus resistors for the common base biasing network. The value of that upper resistance and the value of the pot itself are not very important, and just what I had on hand. What is important to note is that this biasing network does not need to be high impedance for our common base to work properly. In fact, we want the impedance from the base to ground to be as low as possible at our operating frequencies, which is why I've put this fourth capacitor, C4, there. We'll revisit C4 in a bit. So I've labeled the node between the common emitter's Q1 collector and the common base's Q2 emitter as VC1, denoting voltage of collector 1, and a question mark for the DC voltage there. You might be wondering how we determine the quiescent voltage of VC1. Fortunately, it is actually very simple. So long as VC1 is kept a little above the Q1 base voltage so that Q1 is in the forward active region, then the current through the Q1 collector is pretty much entirely determined by the voltage between its base and emitter. And so long as we put a voltage on Q2's base that is a little higher than 0.7 volts above Q1's base, then both Q1 and Q2 will be in the forward active region, and Q2's collector current will be pretty much the same as Q1's collector current, and determined by Q1. So changing Q2's base voltage won't change the Q2 collector current really, it only has the effect of moving around the emitter voltage. So if we recall, in order to keep a BJT solidly in the forward active region, we decided that a collector emitter voltage of 3 volts or higher is our target value. So we left 3 volts for the common base when we designed the biasing for the common emitter. Now it's time to set the biasing voltages so that we have 3 volts across both collector-emitter node pairs. Firstly, we can keep the Q1 emitter at 1 volt, as that keeps our collector current what it was before. This also means the base voltage is the same as it was before. We rename both of these nodes to include the subscript 1 to denote transistor Q1, as we now have 2 transistors. Now we look at the collector voltage for Q2. We note that given our collector current and Q2 collector resistor are the same as in the common emitter case, the voltage at Q2's collector is decided for us, and is equal to what the collector of Q1 was in the previous configuration. 29.55 minus 22K times 1 milliamp is 7.55 volts. So the voltage between the Q2 collector and the Q1 emitter is this 6.55 volts from before. So to give us some dynamic range on the output without cutting into our 3 volt minimum VCE, we want to put 3 volts across Q1 and the remaining voltage of 3.55 volts across Q2. This is because changes in the output voltage are not going to affect VCE1 much at all, since the common base is current buffering and thus shielding VC1 from much voltage swing, which is sort of the whole point of the Cascode circuit. So to get 3.55 volts across Q2, we need to set VE2/VC1 equal to 4 volts. At this point, we can use our 0.7 volt VBE assumption to calculate the Q2 base voltage. Though note that when I tweak those potentiometers, I measure the emitter voltage because for both transistors that is the voltage of importance. The Q1 emitter voltage sets the Q1 emitter current, which is approximately equal to the Q1 and Q2 collector currents, and the Q2 emitter voltage sets the Q1 and Q2 collector emitter voltages, which are the important voltage differences to set in the biasing. And we note the collector emitter voltages for both transistors for completeness. So now that we've gotten the DC voltage out of the way, let's go through the small signal parameters and briefly justify that they're about the same, or make adjustments that we have to make. First, the collector current is defined by the Q1 emitter voltage, so that's the same. Beta is also mostly dependent upon the collector current, so long as our collector emitter voltages are reasonably high, which they are, so that's the same. Now that we've established that beta is high, and that the collector current is the same, we can say that most of the other stuff is also the same. The transconductance, Rm, alpha, Re, Ro, and Rpi are all the same. We're assuming that Q1 and Q2 are very similar, are biased very similarly, and thus have the same high beta, the same alpha, and the same Ro. We also have set Rc and Rs to be the same. This just leaves the gain. So I will make one note here. We're making some approximations here for the gain, assuming that the whole current gain of the common base equals 1, which only occurs if we assume alpha is approximately equal to 1. So I'm not going to go into all the slight deviations that occur. They are small enough that we can ignore them. So the gain remains the same as in the common emitter as expected. Looking at the three capacitors, it's trivial to see that for C1 and C2, which are the 20 microfarad and 1000 microfarad respectively, the situation has essentially not changed, so they remain the same. For C3, that scope probe impedance is still the only impedance that matters, so it hasn't changed either. So all three capacitors are the same as well. Now finally, we return to C4, the last parameter to design. The common base works best when the base is grounded, but as we've learned, when trying to approximate a short circuit, we must be approximating it with respect to some other impedance somehow connected to that shorted impedance. The idea is that the common base essentially has a resistive divider splitting the emitter voltage to ground between Rpi and the impedance of C4. We want that C4 impedance to be much smaller than Rpi so that approximately all of the emitter voltage is across Rpi, maximizing the effectiveness of the common base. Rpi we have calculated here to be about 2.586K, so we need the capacitive reactance to be less than or equal to Rpi at 10 Hz. So, recalling the equations for the previous calculation for the capacitance, we see that C4 needs to be greater than about 6.15 microfarads. I actually made an error when I built the circuit, but fortunately the error was that I assumed I needed 10 times this value, which only really made things even slightly better, though it was definitely overkill. So I used a large 100 microfarad electrolytic capacitor in parallel with a 10 microfarad ceramic capacitor, so C4 is set to 110 microfarads. So now we have all the parameters set. And surprise, surprise, from an AC perspective, this Cascode Lab setup is virtually identical to the common emitter lab setup. So we're all set to do an apples-to-apples comparison of the bandwidth. So first, let's go back to the common emitter lab setup. Here's a picture of the circuit in the lab. The upper portion is the common base and is currently bypassed, so only the common emitter is set up. Let's quickly review our estimated gains. First, we have the common emitter gain, denoted as AVCE, which we calculated was about negative 498.2 volts per volt. Then we have the divider gain I've noted here with AVDiv, which we've designed to be a factor of 1 over 101. The net gain we'll observe on the oscilloscope is the product of these two gains, which comes to a value of about 4.933 volts per volt. Next, let's measure the DC values of these transistor node voltages. The values we calculated are on the left. With my DMM, I get an emitter voltage of approximately 1.002 volts as designed, with a base voltage of about 1.626 volts, a collector voltage of about 7.8 volts, and a VCC of about 29.52 volts. And of course, the resulting VCE is about 6.798 volts. Before we measure the common emitter gain characteristic, we first need to measure the divider gain. Here I've briefly disconnected the divider from the circuit and moved channel 2 of the oscilloscope to the output of the divider so we can measure the divider ratio. I have put averaging on to eliminate noise spikes, and I use peak-to-peak values which automatically eliminate any DC offsets from the calculation. We see a peak-to-peak input voltage of 14.178 volts and a peak-to-peak output voltage of 138.84 millivolts. This is an attenuation factor of approximately 102.1, which is very close to our expected value of 101. We'll use this value for our measured value, as it is a nice low frequency but not too low frequency value of 1 kHz. Just to see how it fares over frequency, we measure the divider again at 1 MHz. We get a peak-to-peak input voltage of 14.189 volts, and a peak-to-peak output voltage of 141.96 millivolts. This is an attenuation factor of approximately 99.95, so still pretty close to 101. So this divider is pretty flat over our frequencies of interest. Now let's measure the overall gain of the system and back out the common emitter gain. Here I've reconnected the divider to the rest of the circuit, and we have the two oscilloscope channels set up as they're shown in the schematic again, so the circuit is properly set up as shown. Sending a 100 Hz sine wave through the system with the input amplitude set so that the peak-to-peak voltage on the output is roughly 500 millivolts, we can now calculate the overall gain of the circuit. We see that the input in yellow shows a peak-to-peak voltage of about 81.07 millivolts, with the output in magenta at 477.8 millivolts. This produces a gain of approximately 5.89 volts per volt. Using this method, I gathered data at 1 kHz, 5 kHz, 10 kHz, 50 kHz, 100 kHz, 500 kHz, and 1 MHz. Here is a table of the values measured and the resulting net gains at each point. I will use 1 kHz as our gain value, as at that frequency we're very far from the corner frequency of the first pole, and all the bypass and AC coupling capacitors are firmly in the short circuit regime, so it is likely the most accurate set of mid-frequency values. So the net gain is about 5.93. Why is it higher than our estimate even though the attenuation is slightly higher? That is likely due to beta being higher than our estimate of 100, and therefore increasing our pi and reducing the impact of the source resistance on the gain. Finally, using our divider gain, we can calculate the common emitter gain without the divider, which is about negative 605.5, higher than our estimate, again likely due to a higher than estimated beta value. So looking at the gain, we see that it rises slightly as frequency increases. This is likely due to one or more of my large capacitors actually being electrolytic capacitors, resulting in a relatively high equivalent series resistance, even at high frequencies. That high ESR is being bypassed by much lower ESR ceramic capacitors in parallel, thus leading to better performance in the mid-frequency range. However, as expected, the gain starts to attenuate around 50 kHz and becomes very small once we get to 500 kHz. We'll look a little more closely at these results once we've run the same tests on the Cascode and can compare them. Now let's move on to the Cascode test. Here's the circuit schematic and a picture of the setup on my breadboard in the lab. Here we have the estimated gain values, which are the same as for the common emitter, and the estimated DC values for both transistors in the Cascode circuit that we discussed earlier. I will use the same measured divider value as with the common emitter because nothing has changed there. As for the DC node voltages, using my DMM, I set the Q2 emitter to approximately 4.003 volts. Q2 base measures at about 4.631 volts. Q2 collector measures 8.08 volts. Q1 emitter is set to approximately 0.995 volts. Q1 base measures about 1.621 volts. And Q1 collector is the same as the Q2 emitter, so 4.003 volts. VCC is at about 29.52 volts. And we have collector-emitter voltages of about 3.008 volts and 4.077 volts respectively for the two transistors, so we should be good to go. Using the same method as I used with the common emitter, I get the following table of gain values over frequency, where I try to set the output at around 500 millivolts peak to peak in the low frequency, high gain region. I will again use 1 kHz as our mid-frequency gain value. So the net gain is about 6.35. Why is it higher than our value for the common emitter? This is due to a useful aspect of the Cascode I didn't actually discuss in this series of videos, that the Cascode can effectively increase the collector resistance to much higher than RO. So the common emitter's effective collector resistance was 22K in parallel with RO. The effective collector resistance for the Cascode is 22K in parallel with a much higher resistance. So that can improve the gain slightly in our situation, and is a much more important effect for active loads. Again, using our divider gain, we can calculate the common emitter gain without the divider, which is about negative 648.3, higher than the common emitter, again likely due to the Cascode improving the effective collector impedance. So looking at the Cascode gain, it also rises slightly as frequency increases. This is similarly due to the electrolytic capacitor's high ESR. The gain of the Cascode starts to attenuate between 100 kHz and 500 kHz, which, recalling the table for the common emitter gains, is a higher frequency than for the common emitter. Furthermore, the gain is over 5 times higher at 500 kHz for the Cascode than for the common emitter. Now, I provide these tables to show that you can perform manual measurements of bandwidth with a scope and function generator, though it is generally faster and easier to use a frequency response analyzer or something similar. I have a function generator accessory for my oscilloscope that I can use to generate Bode plots with the scope in a similar manner to a frequency response analyzer, though with somewhat lower performance. So using that, I made a Bode plot for both the common emitter and cascode, then adjusted the gain after the fact by eliminating the attenuation produced by the resistive divider to get the gain of the common emitter circuit alone versus the gain of the cascode circuit alone. And here we see the results. I have also added the values I gathered manually from the tables shown earlier as those little X's in the plot. And we see the table values match up pretty well with the automatically gathered values. Now we can clearly see a higher bandwidth from the cascode, but we'd like to quantify this in a nice, simple way. One of the simplest ways to do this is to compare the negative 3 dB points of each circuit, which is the point at which the gain drops by about 3 dB. This essentially shows how much higher the frequency of the dominant pole of one of the amplifiers is from the dominant pole of the other amplifier. So zooming in, we sort of roughly see that the gain of the common emitter is about 56 dB at midband, and the gain of the cascode is about 56.5 dB at midband. So the negative 3 dB points of the common emitter and cascode are therefore 53 dB and 53.5 dB, respectively. The frequency at which the common emitter hits 53 dB is about 57.683 kHz. And the frequency at which the cascode hits 53.5 dB is about 391.311 kHz. I will note one more frequency, as given the configuration of this system, it's a little more fair to assess the frequency at which the cascode hits the same gain as the common emitter, since the slight increase in gain due to collector resistance would also tend to make the bandwidth slightly smaller as well. So the cascode hits 53 dB at about 434.723 kHz. However, even using the lower frequency value at 53.5 dB, the cascode is conservatively a little over 6.7 times the bandwidth of the common emitter in this situation. This is a significant improvement and is very effective. A few final concluding remarks for this mini-series. So, the common base is a lesser used circuit in discrete transistor circuits. It tends to shine more inside integrated circuits. Its primary use is as a cascode to either improve bandwidth and/or increase active load impedance. In this mini-series, I wanted to introduce the common base and demonstrate some of its capabilities, but I didn't go in depth on all the advantages and disadvantages of the cascode, such as increasing an active load's impedance. Even though the common base is generally for integrated circuits, it can still be leveraged in niche discrete circuits. Most low and mid-frequency amplifiers in discrete circuits tend to revolve around op-amps, for good reason. Sometimes op-amps need to be augmented in order to have good properties for niche situations, like high-voltage circuits or higher power. So long as you understand how to stabilize and compensate op-amps, using a common base or a cascode may be a good augmentation strategy. Additionally, high-frequency circuits often cannot rely upon an op-amp core due to the inherent problems of high gain at high frequency and high-frequency feedback. The cascode may be usable here to improve gain for high-frequency discrete transistor circuits. All in all, it is useful to understand the common base in the discrete design domain, at the very least because it helps you better understand the internals of some integrated circuits you are working with, and it may even be a useful tool in your belt when designing PCBs. That concludes this video, and the mini-series on the common base. So in this transistor tutorial series, we've introduced the 3 fundamental single transistor BJT circuits and demonstrated them in the lab. I don't know what the next video in this series will be, but I think I'll be focusing on more niche content on this channel for the next few videos, as there are a great many good videos on YouTube regarding the fundamentals of transistors already that you can explore. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have any comments or questions, leave a comment. See you next time.